Hi, now today we're going to look at estimating a definite integral. That is, we're going to look at estimating the area between a curve, and the x-axis. And now the technique we're going to look at involves what we call a Riemann sum. Now in our textbook this is section 4.3. Now in a later video we're going to look at a technique using trapezoids to estimate the area between the curve and the x-axis. And now today we're going to look at using Riemann sums. Now Riemann sums involves using rectangles. So a series of rectangles to estimate the area between the curve and the x-axis. We're going to use what's called an LRAM, an RRAM, and an MRAM. So three types of Riemann sums. The first one is what's called an LRAM. Now that's an abbreviation for a left rectangle approximation method. So if you can imagine a curve, right? Here's our curve, and now with this technique with our curve here, we're going to just kind of illustrate. We're not going to actually estimate the area here. We're just kind of illustrating what an LRAM is, or a left rectangle approximation, or what we call a left-hand Riemann sum. That's what I'll call it. We're going to estimate the area between from the curve to the x-axis from 0 to 14, and we're going to use 7 rectangles. Now in a left rectangle approximation, when you look at this first rectangle, so we're going to draw a series of rectangles that between the curve and the x-axis. Now, in the first rectangle, you notice that the top left-hand corner of that first rectangle, starting at x equals 0, touches your curve. So the base of this rectangle is 2. The height of the rectangle is where that left-hand corner touches your curve. Right, now the second rectangle, once again the base is 2, the base goes from 2 to 4, so the base of the rectangle is 2. The height of the rectangle is the point where the top left-hand corner touches your curve. And then you got the next rectangle, and then the next rectangle. Now you notice on my curve here, the first part of the curve is increasing from left to right, and then it starts to decrease. Now on an LRAM, or a left-hand Riemann sum, as the graph is increasing from left to right, you notice you have these triangular regions between the rectangle and the curve that are not included in our estimation. So in a left-hand Riemann sum, or an LRAM, if we use an LRAM on an increasing function, it's going to underestimate the area. Now as the curve starts to decrease, here's our next rectangle. Now this time you notice once again the top left-hand corner of the rectangle touches the curve, and the base of the rectangle is 2. So the base goes from 8 to 10. So the base of the rectangle is 2 units, and the height of the rectangle is where the left-hand corner touches the curve. Now this time you'll notice that part of the rectangle is above the curve this time. Same thing on the next rectangle, and then the last rectangle. So as the curve starts to decrease with a left-hand Riemann sum, or an LRAM, part of the rectangle is above your curve. So if the curve is decreasing, a left-hand Riemann sum is going to overestimate what would be the actual area. So in a left-hand Riemann sum, again, the height of each rectangle is the value of the function at the left endpoint of each subinterval. Now notice that on a left-hand Riemann sum, at x equals 0, so we're estimating the area between 0 and 14 if we were actually going to get the area. On the first rectangle, at x equals 0, the height of the rectangle will be the function at 0. And you notice at the other end of the upper bound, if you will, at 14, 14 is so at 14, so 14 would actually not be used in a left-hand Riemann sum. Now the other type of approximation is what's called a right rectangle approximation, or a left-hand Riemann sum, or an RRAM. Now here's our curve again. Now in an RRAM, each rectangle, the top right-hand corner of each rectangle is going to touch your curve. All right, so at x equals 0, the top left-hand corner does not touch your curve. So the x equals at x equal 2 is where the rectangle, the top of your rectangle, actually touches your curve. Now also you'll notice as I draw these rectangles, you see these rectangles come up on your screen. Okay, you notice on an RRAM, on a right rectangular approximation or a right Riemann sum, or Riemann sum, as the curve is increasing, part of the rectangle of each rectangle is above your curve. So if the function is increasing from left to right, an RRAM will overestimate what would be the actual area. And then you can see as the curve starts to decrease, this time you have these little triangular regions between the rectangle and the curve. Okay, on a decreasing function, an RRAM, or a right rectangular approximation, is going to underestimate the what would be the actual area. So in an RRAM, or using a right rectangular approximation, the height of each rectangle is the value of f at the right endpoint of each subinterval. So you notice that at x equals 0 will not be used in the approximation, but x equals 14, that right-hand corner of your rectangle, the x equals 14 touches your curve, so that will be used in our approximation. So x equals 0 will not be used in an RRAM, but x equals 14 will be used. Now, the third method, or the third type of Riemann sum, is what we call an M-point rectangular approximation method, or an MRAM. Let me bring the curve back up here. Now, an M-point rectangular approximation, or an MRAM, okay, this time the midpoint of the rectangle is going to touch your curve. So the base of the rectangle is still 2. So if you look at this first rectangle here now, the base of the rectangle goes from 0 to 2, so the base of the rectangle is 2, but the height of the rectangle is going to be the midpoint of the rectangle. So the height of the rectangle will be the function at 1. So the base is 2, but it would be the function at 1 would give us the height of a rectangle. And you can see the midpoint of each rectangle is going to touch your curve. Now also you'll notice that on a midpoint rectangular, on an MRAM, like you see illustrated here, part of the rectangle is above the curve, part of the rectangle is below the curve. So you have a region, a corner of the rectangle that's overestimating, and part of the rectangle is underestimating. So typically, usually, not always, but a midpoint rectangular approximation, or an MRAM, will be the most accurate of the three methods. It's also the most complicated calculation, because you have to find where that midpoint area, or that midpoint of the rectangle, is located. So the height of each rectangle is going to be the value of the function at the midpoint of each subinterval. So let's go take a look at an example. Now with this first example, we're going to estimate the area using all three techniques. So we're going to estimate the definite integral using the indicated method. Now we're going to estimate this definite integral here. All right, so the integral is 1 over x, and we're going to estimate the area between the curve and the x-axis from 1 to 4. And we're going to use all three types of Riemann sums. We're going to use an LRAM, an RRAM, and an MRAM. So we're going to use all three, and we'll see which one is actually the closest to what the accepted area would actually be. Now, if you look at the graph of 1 over x, that looks like so. So this is our graph. Now the lower bound is 1, the upper bound is 4, so we're talking about this region here, from 1 to 4. Now, keep in mind, the more rectangles we use, the more accurate our estimation will be. But we got to find the area of every single rectangle and add them all together. So the more rectangles you have, the more complicated and the more difficult your calculation will be. Now, we have graphing calculators, so to help us with these calculations. So, in this day and age, it isn't that big of a deal. But, before the advent of calculators, it was actually a pretty big deal. But we're going to calculate the area between the curve and the x-axis from 1 to 4 of the graph of 1 over x. So you can see the graph. All right, so let me bring this over to our next slide here. Now, once again, here's our integral. We're going to estimate the area between the curve and the x-axis from 1 to 4. Now, with this first, let's use a right-hand Riemann sum, or an RRAM, with 6 subintervals. Now, 6 subintervals means we're going to use 6 rectangles from 1 to 4. 6 subintervals. Now, first thing we need to calculate is the interval, or what would be the base of each rectangle. Now, to get the base of your rectangle, or the interval, if you will, so the base, okay, we're going to subtract 1 and 4, so the upper bound minus the lower bound, divided by the number of subintervals, so divided by 6. So 4 minus 1 divided by 6, which is 1/2. So the base of a rectangle is going to be 1/2. So every 1/2 increments now, we're going to have to do another rectangle. Now from 1 to 4. All right, now keep in mind, now the area of a rectangle is its base times its height. Now the more rectangles we use, the more times we'll have to use the area formula for a rectangle. Now the base is always going to be one height, but the height of the rectangle will change. Now this is an RRAM, a right-hand Riemann sum. So the right-hand corner of each rectangle is going to touch our curve. So the first rectangle, so we bring it on over here. Now once again, the interval or the base is 1/2. And the rectangle, or the approximation, is going to start from 1 to 4. So the first rectangle will look sort of like this. All right, so from 1 to 4. The second rectangle will look sort of like this. So the second rectangle, the first rectangle goes from 1 to 1.5. The second rectangle goes from 1.5 to 2. And you'll notice now on the first rectangle, the height of the rectangle, the rectangle actually touches the curve at x equal 1.5. So then you get the second rectangle. So we got our second rectangle. Let's bring it in. And then the next rectangle, and the next rectangle. Now we're going to have 6 rectangles altogether. Here's the next rectangle, and then the last rectangle. And that's kind of difficult to do on the PowerPoint here, but the right hand corner, the top right hand corner of each rectangle should touch our curve. So as we calculate our area, looking at just that first rectangle now, the base of the rectangle is 1/2. Now the height of the rectangle is going to be the function at 1.5. So that's going to give us the height of a rectangle. So if we're going to calculate the area of the first rectangle, it will be 1/2 times the function at 1.5 plus, and then we do the next rectangle. Now the second rectangle goes from 1.5 to 2. Now at x equal 2, the right-hand corner of the rectangle touches the rectangle, so the height of the rectangle. So the next rectangle would be 1/2, that is the base, times the height, which is the function at 2.0. The next rectangle will be base times height, 1/2 times the function at 2.5. Now once again, we're just adding 1/2 each time, or adding 0.5 each time. Now the next rectangle will be 1/2, that is the base, times the rectangle or the function at 3.0, and then 1/2 times the function at 3.5, and then 1/2 times the function at 4.0. Now you notice now on a right-hand Riemann sum, okay, we do not do a calculation at 1. Okay, we start at 1.5, not at 1, because the right-hand corner of your rectangle is where it touches your function. So let me bring this calculation on over to the next slide now. Now one thing you can do, to instead of multiply by 1/2 over and over again, you can just factor 1/2 off your calculation, and this is what it becomes. So 1/2 times the function at 1.5 times the function at 2.0, etc. All right, so this will be 1/2. Now the function at 1.5 is 1 over 1.5. Now remember, the original function is 1 over x. So when you calculate the function value at 1.5, that's simply you substitute 1.5 in for x. It'll be 1 over 1.5 plus the function at 2 would be 1 over 2. So remember, our original function is 1 over x, so just substitute 2 in for x. Okay, plus the 1 over 2.5 plus 1 over 3, 1 over 3.5, 1 over 4. Now you're going to add all those together times 1/2. Now, if you have a graphing calculator or a calculator of some type, this is a pretty simple calculation. You get an approximation of 1.218. Okay, let's take the same problem and let's estimate the area again. Now you notice now the problem we just did was a right-hand Riemann sum on a decreasing function. The approximation that we just looked at would have been an overestimation. It would have been an overestimation of what the actual area would have been. Now this time let's use a left-hand Riemann sum with 6 subintervals. Now this time the left the top left-hand corner of each rectangle is going to touch our curve. So once again, we're estimating the area from 1 to 4. So the first rectangle, okay, once again, the base of the rectangle is going to be 1/2. But this time, the top left-hand corner is going to touch your curve. So the height of this rectangle is going to be the function at 1. The base is still 1/2. Okay, this will be the next rectangle. You can see the top left-hand corner of the second rectangle touches the curve at 1.5. And then the third rectangle and the fourth rectangle. Right on down the line, we have 6 rectangles. There they are. Now you notice now a left-hand Riemann sum, or an LRAM, on a decreasing function. You can see part of each rectangle is above your curve. So when we do this estimation should overestimate the actual area. So we're going to get an area that should be greater than the actual area between the curve and the x-axis. Now, looking at just the first rectangle, the base of the rectangle is still 1/2, and that's going to be the base of each rectangle. Now, the height of this rectangle is the function at 1.5, or 1.0. Now, you notice now the RRAM, the right-hand Riemann sum, started at 1.5. This one starts at 1. So on the left-hand Riemann sum, we're going to use the 1 in our function. So to calculate the area of the first rectangle would be 1/2 times the function at 1 plus the second rectangle is 1/2 times the function at 1.5 plus the function 1/2 times the function at 2, 1/2 times the function at 2.5 plus 1/2 times the function at 3 plus 1/2 times the function at 3.5. Now you notice we do not do 1/2 times the function at 4. Right, because this is a left-hand Riemann sum, so that very last endpoint, from 1 to 4, that very last number there is not used in the calculation. The 1 is used to calculate the area of the first rectangle, but the 4 is not used in a left-hand Riemann sum. So let's bring our calculation on over. Now I'm going to factor 1/2 off of each. Now this time we're going to substitute 1 into our function for x. Now the original function is 1 over x. So we have 1 over 1 plus 1 over 1.5 plus the function at 2. Now that just means we're going to substitute 2 into the original function, which is 1 over x. So it'll be 1 over 2 plus 1 over 2.5 plus 1 over 3 plus 1 over 3.5. Now this is the part where you want to grab your calculator and see if you get the same thing that I got. Now when I did my approximation, I get 1.593 for the estimation. Now keep in mind, this is a left-hand Riemann sum on a decreasing function, so that's going to be an overestimation. This is going to be greater than the actual area between the curve and the x-axis. So let's try the third technique. Now the third technique we're going to use here is what's called a midpoint Riemann sum. Once again, we're going to use 6 subintervals from 1 to 4. So the first rectangle will look like this. Now once again, the base of the rectangle is still 1/2, but this time the height of the rectangle is going to be the middle of the rectangle. Okay, this will be the second rectangle, and then the third rectangle. I'm going to use 6 rectangles because we have n equals 6, so 6 subintervals. That means simply means we're going to use 6 rectangles. Now on the first rectangle, now you'll notice the base of the rectangle goes from 1 to 1.5. So the middle of that rectangle, well, the base of the rectangle is still 1/2, but the middle of that rectangle is going to be at 1.25. So the height of the rectangle will be the function at 1.25. Now the second rectangle would be at 1.75. So you're just adding 0.5 each time to get the midpoint of the next rectangle. So the area of the first rectangle here will be 1/2, that is the base, times the function at 1.25. Plus, the area of the second rectangle would be 1/2 times the function at 1.75. The area of the third rectangle is 1/2 times the function at 1.25, plus 1/2 times the function at 2.75, plus 1/2 times the function at 3.25, plus 1/2 times the function at 3.75. So you're just adding 0.5 each time to get the midpoint, where the function touches the midpoint of the next rectangle. So let's bring that calculation over to the next slide here. The function, now I'm going to factor 1/2 off. Now the function at 1.25 would be, let's bring that on down here, so we're just factoring 1/2 off. That will be 1 over 1.25. Remember, the original function is 1 over x, so we'll just have to substitute 1.25 in for x. It'd be 1 over 1.25 plus 1 over 1.75 plus 1 over 2.25, 1 over 2.75, 1 over 3.25, and 1 over 3.75. That's the midpoint of each rectangle there, substituted into your function for 1 over x. Now, we'll grab our calculator, and this is what the approximation will be. Now remember, in a midpoint, in an RRAM, or a midpoint Riemann sum, part of the rectangle is above the curve, part of the rectangle is below the curve. So usually this is going to be the most accurate of the three methods. Now, also on the PowerPoint, the accepted approximation. Now you can do this on a graphing calculator, very, very easy to get the actual area. So what we call the accepted approximated area is about 1.386. Now if you compare this to the other two, or to all three methods, you can see clearly that the midpoint Riemann sum was definitely the most accurate of the three. Now let's go on to example number 2. Now this time let's try another midpoint Riemann sum. Now midpoint Riemann sum typically for most students is the most difficult of the calculations, because now you have to use the midpoint of your rectangle to get the height, what would be the height of the rectangle. So a midpoint Riemann sum is the most difficult, so let's try one with 5 subintervals to estimate a definite integral. So let's try the integral of cosine x from 0 to 1. Now when you look at this definite integral, this is the definite integral from 0 to 1 of cosine x. So remember we're going to estimate the area from 0 to 1 of the function cosine x. Now let's get our interval, or what would be the base. This is going to be the base of each one of our rectangles. Now we're going to use 5 subintervals. That means we're going to use 5 rectangles. So we're going to do 1 minus 0 divided by 5. Alright, so 1 minus 0. So basically we're going to subtract the upper bound and the lower bound, and then divide by the number of rectangles. So divided by 5 gives us 1/5, or 0.2. I didn't put 0.2 here on the PowerPoint, but it's just 0.2. So bringing this on over, here's our interval again. So I have an interval of 1/5. As you look at your curve, the cosine curve from 0 to 1 is definitely decreasing from left to right. So the first rectangle now is the base of the rectangle will go from 0 to 2. So this is the first rectangle, and this will be the second rectangle, and the third. You got your fourth rectangle and the fifth rectangle, and you can see part of the rectangle is above the curve, part of the rectangle is below the curve. So this should give us actually a pretty accurate estimation for the area between the curve and the x-axis. Now, just looking at the last rectangle here, well, actually the midpoint of the first rectangle will be the base of the rectangle goes from 0 to 0.2. So the middle of the rectangle is going to be at x equals 0.1. Now, if you're not for sure how to get that, just add the 0 plus 0.2 and divide by 2, and it will give you that midpoint. Now from here we just have to add 0.2 each time to get the midpoint of the next rectangle. Now the second rectangle would be 0.1 plus 0.2, or 0.3. The next rectangle, the midpoint of the next rectangle, it is where the rectangle is going to touch your curve, the top of the rectangle, would be 0.3 plus 0.2, which is 0.5. The midpoint of the fourth rectangle will be 0.7. Now we're just adding 0.2 each time. And the last rectangle is 0.9. Now just looking at that last rectangle down there, we're going to get the base and the height of that rectangle. The height of the rectangle will be the function at 0.9. So that's going to be the height of the rectangle. Basically, you substitute 0.9, it is the midpoint of the rectangle, into cosine. Now the base of the rectangle is, I didn't put this down, I didn't put this on the PowerPoint, is 0.2. So the calculator area, 0.2 would be the base. So it'd be 0.2 would be the base of the rectangle times cosine is 0.1 plus cosine 0.3 plus cosine 0.5 plus cosine 0.7 plus cosine 0.9 times 0.2. Now, if you have your calculator, make sure your calculator is in radians, not in degrees. Right? So the estimation here is about 0.843. Now, the actual area. Now for anybody that knows how to use the fundamental theorem of calculus, you can calculate the area from 0 to 1 of cosine x very easily, or you can do it on your graphing calculator. The actual area is 0.841. You can see how close the MRAM, the midpoint rectangle approximation, came to the actual area between the curve and the x-axis. So it's actually a very close approximation. Now, let's try another example. Now, this time, let's just try a left-hand Riemann sum with 6 subintervals again. And this time, let's try this definite integral here. So we're going to estimate the area between the curve and the x-axis from 0 to 6. Of 3 plus 2 sine x. Now we do another trig function. Those are, typically can be a little bit more difficult for some students than this polygonal type function or something. But we're going to try another trig function. Now the interval, that would be remember this is going to be the base of a rectangle. It goes from 0 to 6, so it'll be 6 minus 0 divided by 6. You get 6 subintervals. Now remember the number of subintervals is going to be the number of rectangles we use. So when you see 6 subintervals or n equals 6, that simply means we're going to use 6 rectangles. All right, so our base of a rectangle is going to be 1. Now, if you look at the graph of 3 plus 2 sine x, it looks something like this here. So once again, we're going to estimate the area from 0 to 6, and we're going to use a left-hand Riemann sum of LRAM. So remember now, in an LRAM, the left-hand corner of the first rectangle is going to touch your curve. Now, the base of that rectangle goes from 0 to 1. So the base of the rectangle is 1. The height of the rectangle is the function at 0. So to get the height of that rectangle, we would substitute 0 into our function for x. Now, this would be the next rectangle. So once again, the left-hand corner of the rectangle is going to touch the function. Okay, this will be the next. This will be the next. And once again, we're going to use six rectangles. Now, you notice now, on some rectangles, is going to underestimate the actual area, and then some rectangles, you have the little triangular area region above the curve, and it'll overestimate. So we'll see how accurate this method is to the actual area here in just a minute. Now, so to set this up, now remember the base of each rectangle is going to be 1. So I'm going to pull the 1 off. So out front, so it'll be 1 times now we're using a left-hand Riemann sum. So the first endpoint was at 0, so it'd be 3 plus 2 times sine 0 plus 3 plus 2 sine 1. The next rectangle would be at 2, and then 3, and then 4, and then 5. Now notice the 6 is not used in a left-hand Riemann sum. The 0 is. So you're going from 0 to 6. So we're going to use the 0. The 6 we don't use. So get your calculator. Let's do our estimation is about 18.352. Now the actual area is about 18.080. So you can see actually a fairly close approximation. So this is just another example here. This is a left-hand Riemann sum or an LRAM to estimate our area. Now I want to do one more problem. Now this time I'm going to use a data problem. I teach AP Calculus at my high school, and quite often on the AP Calculus exam we see data problems. So actually on the open, there's always, it seems like a data problem of the 6 open response questions. So we're going to do a data problem here. So for students that are that will be taking the AP Calculus exam, you see these types of problems. So let's try this problem here. So the table below shows the velocity readings of a car taken every 30 seconds over a 5-minute interval. So here's our table. So this is so you can imagine a car or something, and we're estimating the velocity of a car taken every 30 seconds. So let's say at the beginning of our time readings at t equals 0, the car was going 60 miles per hour. After 30 seconds, we take the next velocity reading. So looking at the odometer is going to 55 miles per hour. At 60 seconds, the car is going 50 miles per hour. At 90 seconds, 45 miles per hour. After 120 seconds, the car is traveling 40 miles per hour. So as you can see, it's getting slower. After 150 seconds, the car is traveling 45 miles per hour. After 180 seconds, it's going 50 miles per hour. 210 seconds, it's going 60 miles per hour. After 240 seconds, the car is traveling 30 miles per hour. And after 270 seconds, the car is only traveling 40 miles per hour. And after 300 seconds, this is over a 5-minute interval, so that would be 300 seconds, the car is traveling 45 miles per hour. So what is the estimated distance in miles traveled by the car during this 5-minute interval? Now, using a midpoint Riemann sum with 60-second subintervals. So 60-second subintervals. All right. Now here's our data, all lined up. Now remember, the distance traveled is going to be the area under the curve, or the area between the curve and the x-axis. All right. So the first subinterval, we're doing 60-second subinterval. So the first interval goes from 0 to 60. Now between 0 and 60, the midpoint would be at 30 seconds. So in our case, the midpoint, the height of that rectangle would be 55. So the interval goes from 0 to 60. The midpoint would be at 30 seconds, and the height of the rectangle, the midpoint here, would be 55. Now, the next interval goes from 60 to 120. The midpoint is going to be 45. Okay, that would be the height of your rectangle, if you would. Now, a graph may make this a little bit clearer, so if you wanted to, you could actually do a little sketch, and you can see the height of each one. Now, on the third interval, goes from 120 to 180 seconds. The midpoint here would be at 150 seconds. That would be a velocity of 45 miles per hour. The next subinterval from 180 to 240 has a midpoint of 60. And the last subinterval goes from 240 to 30, and you have a midpoint of 40. So we have 5 subintervals. And the midpoints are at 55, 45, 45, 60, and 40. So as you do our calculation, okay, this will be 60 seconds, so it's a 60-second subinterval. So 60 would be the base of your rectangle. So it'd be 60 times 55 plus 45 plus 45 plus 60 plus 40. All right, so 60 times 55, 60 times 45, 60 times 45, etc. Now to do this calculation, now you got to be careful. All right, you're going from you're multiplying 60 seconds times miles per hour. So we're going to have to convert 60 seconds to hours. And to do that, you just have to divide be 1 divided by 60 hours. So 60 seconds is 1/60th of an hour. So it'll be 1 divided by 60 times miles per hour. The hours will cancel. Now, if you don't do this, this conversion, you're going to get like some ridiculously large number. All right, so you get the car traveling like 700 miles in 5 minutes, which is an impossible answer. So you have to make sure, you have to watch that you're multiplying seconds times miles per hour, and you have to convert the seconds into hours. And as you do your calculation, then it'll be 1/60 times 55 plus 45 plus 45 plus 60 plus 40, and we get and the estimation here, the distance traveled, is about 4.083 miles. And like I said, this is you see this type of problem or this type of estimation quite often on on data problems on the AP Calculus exam. So typically they'll have a problem where you'll use rectangles or you'll use trapezoids. So hopefully this will give the students some idea as to how to use a data problem, how to calculate, how to use an MRAM or one of the estimation areas that we looked at today. And that is the end of my video. So hopefully you have found this video helpful in estimating the area between the curve and the x-axis. Now the next video we're going to look at will be a video using trapezoids, so using what's called the trapezoidal method. But hopefully you found this video helpful as far as estimating area between the curve and the x-axis.